This video is for Trig, section 7.2, where we're starting in on some more of those formulas. Remember to keep that note card handy. So these are the sum and difference formulas, and you see a pretty strong pattern here, and hopefully you can even get these memorized pretty quickly. So you'll notice that in the sine, so it's going to be two different signs, so it's going to be kind of hard to say, but sine, S-I-N formulas, the sines, S-I-G-Ns, match. So plus is plus, minus is minus. But in the cosines, they are opposite. The plus is a minus and the minus is a plus. So keep that in mind. It's a really easy thing to mess up. Otherwise, you can notice that in the sines, it goes sine, cosine. In the cosine, it goes cosine, cosine, and then sine, sine. So just keep that in mind. The tangent is a little bit less common, so kind of keep those handy. We do have an example or two, problem or two in the homework using the tangent, but the sine and cosine sum and difference formulas are the more common. So let's try it out. So if I had this right here, I can see that it kind of follows this pattern. So I skim through my note card, I see, oh yep, sure enough, here it is. Here's that sine, cosine, so it's one of these two. It's a minus, so it must match this one. So I can combine them and use going from this form to this form using the sum and difference formula for sine, where this is my A and this is my B. Okay, so really I just have sine of A minus B. It's like so easy, it can be a little confusing at first, but we're just going from this form to this form. I can of course clean that up just a little bit because 5x minus 4x is just x, and that's the answer. So like I said in the identity section when we were starting those, is a lot of times we can just kind of switch forms back and forth as needed to make things a little bit more neat and tidy and cleaned up. So if you had something that looked like this, you could use your knowledge of identities and be able to switch it into this much cleaner form right here. So let's try it again right here. Here I see that there's cosine, cosine, so it's one of these two. Remember that this one was the opposite, so this must be a cosine of A minus B, where this is my A and this is my B. So I'm matching it up right here, okay? So that means it would be the 4x and then the 7x, making a final answer of cosine of negative 3x. And don't worry, you can take the cosine of a negative. Remember, that just goes clockwise instead of the normal, wait, yeah, counterclockwise. So it's all okay. So here we try it with some numbers. These were variable x's, so we were just kind of cleaning up in general. So let's try it out with these numbers. Here's another one that goes cosine, cosine, so it's one of these two. Remember that this one has the opposite in the middle, so this would be a plus. So this would go 15 plus 75. So of course 15 plus 75 is 90, which means I can actually finish this one up because cosine of 90 degrees is something that I know. That's straight up, so that would be cosine of 0. Okay, so the final answer for this problem would just be 0. Now, you might say, when would it ever come up that it would be in this strange form? Now, a more common place to use these would be in something like this, where it's not an exact. So again, back in the day, they didn't have these super awesome calculators that could just find sines and cosines of weird angles for them. They had these big, crazy tables. So if they could make it a combination of some that they did know off of their unit circle, it would save them a whole bunch of time. So in this right here, I say, okay, well, I could use something I know to combine and get 75. So I could say, well, it's 60 plus 15, but I don't know an angle of 15. It could be 90 minus 25, but I don't, or wait, yeah, no, 90 minus 15, but that wouldn't work either. But one that I do know would be a 60, no, not a 60, a 30, and a 45. So you may have to play with your numbers just a little bit, but using all of those that we do know on our unit circle, I kind of go pluses and minuses until I can find some combination. So I could go another direction. I could have gone like 180 minus something. So 180 minus 105 actually could have worked out. So there are multiple ways to get through this problem. But this would be one of the most straightforward. 30 and 45 make 75. So now I'm going to use this form of the formula, taking it from here to here. So I would go sine of A, which in this case is 30, cosine of B, which in this case is 45, plus cosine of A, sine of B. And all of these are things that I know. Sine of 30 on my unit circle is 1/2. Cosine of 45 is the square root of 2 over 2. Plus cosine of 30 is square root of 3 over 2. And sine of 45 is square root of 2 over 2. So I know it looks like a big mess, but there's actually not a whole lot I can do to clean this up. I just combine these right here. 1 times square root of 2 is just square root of 2. On the bottom, 2 times 2, of course, is 4. And then this one, square root of 3 times square root of 2, since they're both square roots, would give me square root of 6. I would combine those inside numbers like that, and the same 4. So I could write it either in this form right here, or I could write it as a single fraction of square root of 2 plus square root of 6, all over that same common denominator of 4. So they're both equally acceptable, just whichever one is easiest to write in XYZ. Personal preference. Sorry, so I can get a circle around these without running over some of my numbers. There we go. All right. So here I have radians, and I know radians are a little less familiar, but once you get to kind of playing with them, they're actually easier. So I see 12ths, okay? I don't have any 12ths on my unit circle. I do have sixths, and I do have halves, so I could kind of play with those. I also have thirds and fourths, so I can kind of play with those to see what would give me a 12th. So what I actually do is I say, okay, let me go big to try to kind of pull apart these pieces and see if I can get something that would add up to be 7/12. So if I took what I knew, sorry, my page right here, of pi thirds, that's the bigger of the two, thirds and fourths. So okay, well let me just try on my calculator, 1/3 minus 7/12. So just kind of hang in with me. Then I see that I actually have negative 0.25. Okay, that is negative 1/4. So what that means is if I took the bigger number, 7/12, minus the smaller one, let's flip it, 7 divided by 12 minus 1/3, that gives me a fourth. So that means a third and a fourth combined make 7/12. Okay, so I'm just kind of playing with the fractions there. So I picked thirds because I knew thirds and fourths were on my chart, and I know 3 times 4 makes 12, and I just kind of played with my numbers until it worked. So I found that the cosine of 7 pi 12ths would be the same as the cosine of pi fourths plus pi thirds. Okay, so I took the one they gave me and I took one that I just kind of picked until I could make it work out. Luckily, it just kind of worked out that first time. If I'd tried sixth, I might have said 7/12 minus 1/6. It gives me 5/12. So I say, oh, that didn't really help me. So you just kind of play with those numbers until you can get two that you do know that are on your unit circle. So now I'm going to use this formula here. Remember that it's that opposite sign in the middle. So I'm going to break it down using these ones that I already know. So that would give me cosine of the pi fourths, and then cosine of the pi thirds, and opposite sign, so minus sine of the pi fourths, sine of the pi thirds. These are all things that I know on the unit circle, so I go find those. Cosine of pi fourths, just like this last one, was the square root of 2 over 2. Cosine of pi thirds is 1/2. Sine of pi fourths is the same square root of 2 over 2. And then sine of pi thirds is the square root of 3 over 2. Looks pretty familiar, doesn't it? So you'll find a lot of these kind of tend to reappear in these problems. So it's almost exactly the same as our last problem where I have the square root of 2 over 4 minus the square root of 6 over 4. Or again, you could put it all in one big fraction as square root of 2 minus square root of 6, all over the same common denominator of 4. Either one of these two answers is equally acceptable. Okay. Now in the next ones, they're actually trying to combine some problems that we've already done in the past. Wait, nope, sorry. Before we get to that one, let's do this tan. So the tangent one right here, is that less common formula, so we're going to use this guy right here. So tangent of 165. So I need things that would add up from the ones we know on our unit circle to give us 165. So that's a bigger number. Let me see what 165 minus 90 is, because I know 90. That'll give me a hint. I say, oh, that's 75. I kind of already know that. So let me see if I did 90 and 30. So 90 plus 30 is 120. 165 minus 120 is 45. So there we go. There's some I know. So that means this could be written as tangent of 120 plus 45. And now again, this is not the only one that would work. So this was just me playing with numbers till I found two that I did know on the unit circle. This is a plus, so I'm going to use this guy right here. So I'm going to go tan A. So tangent of the first one, 120, plus tangent of the second one, 45, over 1 minus tan A tan B. Tan 120, tan 45. Sorry, I know it's kind of squished in here. Okay, now remember the tangents aren't on the provided unit circle, but if you haven't already, it's actually pretty handy to go ahead and fill in the tangent of each of those known values by dividing sine and cosine. So you just take the known sine and divide it by the known cosine and get those fractions. And that should give you that the tangent of 120 is actually just the square root of 3, because those halves flip over and cancel. The tangent of 45, square root of 2 over square root of 2, is just going to be a 1. Okay. And then on the bottom I say 1 minus, same things, so the square root of 3 and a 1. So it doesn't clean up very much. It would just be the square root of 3 plus 1 over 1 minus the square root of 3. Now it might seem like that should cancel, but it does not. So remember when we learned about our fractions that those plus and minuses change things. So even though it kind of looks like they have something in common, if you think about 5 minus 3 and 5 plus 3, wait, no, that's a bad one. 5 minus 1 and 5 plus 1, that one's kind of bad too, hang on. 4 plus 1 and 4 minus 1, let's do that. So 4 plus 1 is 5, 4 minus 1 is 3, 5 and 3 don't have anything in common. So even though it seems like they should have canceled, they're actually completely different numbers. All right, so this one right here, we kind of go back into some of our problems that we learned back in the day. So we need to use our triangles. So in my formula, sine of A plus B, I have A's and B's. Okay, I'm going to do sine of A and cosine of B. So I'm going to need one of each. So they only gave me the sine of A, which means I need to use my triangles just like we did way back in chapter 1 to find the corresponding cosine. So I'm going to have a triangle for A, and I'm going to have a triangle for B. I will color code them. Let's see, which color's not next to it? Orange. That's kind of close. I'll do blue. Red and blue. Blue. Okay, there we go. So the information that they gave me was that sine of A was negative 4 over 5. Now remember that the sine is the opposite over the hypotenuse. I just completely ignore the negative because they told me that this is in quadrant 4, so I'm going to come back to that later. So don't worry about the signs, S-I-G-N's, right now. So then I would use my quadratic Pythagorean theorem to use the a squared plus b squared is c squared to get this guy. Now you're going to see these three numbers come up a lot. Now my sine of b, opposite over hypotenuse, was 3 and 5. Now if I take 5 squared, which is 25, I always end up with 3 squared plus 4 squared. These come up a whole lot. But just to kind of double check, I would say if this was x, that x squared plus 4 squared is equal to 5 squared. 25 minus 16 is 9, which confirms that the triangle with a 4 and a 5 should also have a 3. So that means this one Same story would have a 4. Okay, so a 3, 4, 5 triangle is really common. So as soon as you see those two numbers, you know the third number. All right, so if you need that work shown right here, it'd be the same story. I would say that y squared plus the known 3 squared equals the 5 squared, which means that y would be 4.